Hello everyone, I'm Mohit Anparu. Uh, Today we are here to discuss about the seminar of our subject signals and systems. And today my topic is classification of basic signals and systems. And what is a basic line is signals and systems are two most basic building blocks of both electrical and electronics engineering. A signal carries information about the behavior of something like sound, temperature, voltage, and a system is a process. If we pass a signal, it takes a signal as an input, and system do some mathematical activity and gives another signal as output and signal as output. So here we can say some common signals are temperature, heat, and sound, voltage. A system is a process or a device. It's a process or device that takes a signal as an input and produces the another signal as output. The signal classifying signal and the systems gives us a shared language. It tells us which mathematical tool apply and uh, which approximates are safe and which are physically implementation are possible. Oh, wait. Moving on to next slide. So what is a signal? A signal is simply a function that conveys information about the behavior, physical quantity. Mathematically, we often write signal as analog signal as x of t, where t is continuous time for analog signal, and for discrete time signals x of n, where n is an integer index. Common examples include an audio waveform, a microphone, a temperature reading from a sensor, or the voltage of at a node in a circuit. Signals can carry sensor readings, speeches, video frames, or encoded digital data. And what is a so what is a system? A system is any rule or device that maps an input signal to an output signal. Formally, we often write y of t equal to delta x of t. Examples are amplifiers, filters, uh, modulators, and communication channels. Systems can scale, shift, combine, delay, or otherwise change signals. Some systems are described by algebraic formulas, differential equations, or difference equations. Others are best understood experimentally by applying known inputs and observed outputs. So, some common examples of y of t equal to x of t plus h of t. It is an example of linear impulse signal, impulse response. And moving on to next slide. So, what is continuous? And so here you can see for continuous time signal, the graph is plotted at every point, so it moves from up to down, and you can see even if we zoom in or see even at a very small point also in the on the for every value of x of t there will be a value of y of t, so it will be continuous. And in the case of discrete, there will be there is no compulsory or there will be no continuous values. So if you see, if we have a -1 here, we will have the values at either 0 or -2 in the next case. In between -1 and 0, there are no values for assigned for this signal. So this is an example of discrete time signal, and this is an example of continuous. So continuous time signals exist for every real value time and are written x of t. Discrete time signals are defined only at the integer terms and are written x of n, so x of t, x of n. Sampling converts a continuous time signal to discrete time signal. So, convert a continuous time signal to discrete time signal, we need to perform sampling for a continuous time signal. So, continuous time signals are needed. Continuous time math identical differential equations, integrals, and discrete sequence are usually difference equations. The choice effect analysis methods are practical implements. So, when so mathematical. Next slide. Periodic and versus aperiodic signals. So, periodic time signals repeats every period t. X of t plus tau equal to x of t for all t. A sample example is a sine wave. Periodicity means the signal has a discrete set of frequencies, harmonics, and a periodic signal does not repeat. Examples are signal sing. So for periodic time signal, we can take sine wave as an example. For a periodic, usually have continuous frequencies content, often req- require different tools for analysis. So moving on to the next slide. Even even and odd signals. A signal is said to be even if the x of t is equal to x of minus t geometrically. It is symmetric about the vertical axis. So here you can see it is symmetrical about the vertical axis, and it is odd signal if the x of t is equal to minus x of minus t. So we can simply find whether the signal is given signal is even if we substitute minus c. If it gives the same value as x of t, then it will be an even signal. If we substitute uh, if we substitute minus t, if it gives a minus x of minus t, then it will be an odd signal. So an odd signals are anti-symmetric. Any signal can be decomposed into an even part and an odd part using x of t equal to 1 by x of t plus x of minus t. For odd signal, x of odd signal t equal to 1 by x of t minus x of minus t. So the difference between is minus in front of x here and the both difference between these two. And next we are going to see about deterministic versus random signal. Deterministic signal are exactly predictable. So for a given time t, we can predict the signal whether what will be the amplitude of the signal, what will how its shape, and we're going to determine. But in the case of random signal, we cannot determine how it will be. How what is it amplitude? We cannot. We can predict this using mathematical forms easily. So the statement goes like this: deterministic signals are exactly predictable. Their values at any time is known as from a formula. Random or a stochastic signal. This is also called as stochastic signal. Stochastic, which is mainly determined using probability terms. Stochastic means probability are described statistically. We talk about mean, variance, and probability distributions. Examples: a mathematical sine wave is a deterministic signal. Thermal noise or many communication channels are random signals. In communication and signal processing, we model noise and fading statistically and design systems to perform well on average or with specific reliability. Okay, that's it. And there is a crucial importance of this both the deterministic signal and the random signal in the communication engineering. So next we are going to see the energy and the power signals. We classify signals and by how their energy or power behaves. The energy of a continuous signal is E equal to minus infinity to infinity x of t square dt. For a discrete signal, replace the integrals with a sum. So summation infinity minus infinity to infinity x of t square mod of x of t square. That's it. A signal with a finite in energy is an energy signal. A power signal has infinite energy but finite average power, defined as the same average of x of t square over an infinite interval over an infinite interval. Periodic signals like a pure sinusoidic are typically power signals. Short pulses are energy signals. The distinction matters when choosing analysis tools. So that's it for this energy. And so next we are going to see analog versus digital signals. Analog signals vary continuously and in amplitude and time. Digital signals are discrete amplitude levels and are processed as number. Real systems are often converts analog to digital using ADCs, then process digitally, then converts back via DACs. So from converting into analog into digital, we will use ADCs. For converting back from digital to analog, we use DACs. Digital processing enables predictability, error correction, and complex algorithms. Analog signals are sometimes preferable for simplicity, low latency, or where quantization is undesirable. So, this is up to what are signals, and next we are going to move about the systems. So, what is linear system? Linear system satisfies superposition theorem. So if inputs x1 and x2 produces output y1 and y2, then the inputs a of x1 and b of x2 produces a of y1 plus b of y2. This let us use convolution and frequency domain methods. Nonlinear systems do not satisfy superposition theorem. So this doesn't satisfy the theorem. If x1 and x2 are passed, we will get then outputs y1 and y2. But in the case of if we multiply this x1 and x2 like a of x1 plus b of x2, we don't is not equal to a of y will not get the outputs as a of y1. So a of y1 and b of y2. So this is the difference between the linear and non-linear systems. Nonlinear systems do not satisfy superposition theorem. Examples include diodes, saturating amplifiers, and many biological systems. Nonlinear behavior can produce harmonics, limit cycles, and typically requires specialized analysis. So that is about linear and nonlinear. And coming about time invariant and time variant systems. A time invariant system responds the same way regardless or of when you apply an input. So time invariant, it doesn't depend upon when you apply the input. The output will not be dependent on the input when you apply the input. Delaying the inputs delay the outputs by the same amount. These systems are simpler to analyze. Impulse response fully characterizes them. Time variant system changes their behavior over time. For example, a filter whose coefficients change or a wireless channel that varies with the movement. Time variant systems are harder to model and may require adaptive techniques. So, going on to next, causal and non-causal. So causal systems outputs at any time depends only on the present input. So if we want for a causal, you can easily say that for the current output that the system is going to generate will be only dependent on the current input. But in the case of non-causal, the current output is dependent on the even the previous output or previous outputs input, previous systems input. So, so you can say a causal system's output at any time depends only on the present and past inputs. This is necessary for real-time physical reliability. A non-causal system can depend on future inputs, such as systems are not physically realizable in time, but are useful in offline processing. For example, when designing zero phase filters that requires future sampling, in practice, non causal designs are implemented with delay or by operating offline. So, on to next slide, slide number 4. Stable and unstable systems. Stability in the BIBO sense mean every bounded input produces a bounded output. For many linear systems, this is equivalent to impulse response being absolutely integrable, continuous in case what integrable actually means, contiguable in case, and absolutely summable, discrete in case. So stable systems are essential for predictable behavior. In control systems, instability can lead to runaway responses and runaway responses. Instability often requires redesign, adding, damping, changing, and controlling parameters. And moving on to the last slide. So this is a summary and to classify to what we have learned is classifying the classification of basic signals and systems about by time domain, periodicity, symmetric, deterministic, energy, power, analog, digital, linear, time variance, causality, and stability tells us which tool to use at what implementation are possible. And these classifications are central to communications, audio processing, control systems, instrumentation, or more and more. And thank you, everyone. I'm ready to, and that's it. Thank you.